All right, let's go ahead and get started. Today we're going to talk about natural language processing. So this is a really cool topic in machine learning. We unfortunately won't have much time to really dive into all the details, so today's lecture is going to be really high level. What is NLP all about? Give you some ideas of how kind of the latest and greatest techniques work. If you're interested in learning more about NLP, there's a course here at UCI that I really recommend taking. It's CS178. It's a grad level class, but if you took this class and did well, then you're more than well equipped to handle that class. It's a lot of work, but not too much math, so if you like NLP, definitely check that class out. It's at CS272. So just a few reminders before we get started. Fifth homework due Friday at midnight, so short assignment, shouldn't be too bad. Your projects are due in 1 week, so hopefully you've made pretty significant progress on those. And as promised, there will be a sample final exam coming out, hopefully by tonight. I'm trying to get my TA to help me write a few questions for that, but yeah, should be out tonight. And then Thursday's discussion section this week is just going to be reviewing the sample final. So go ahead and make sure you attempt that sample exam before Thursday. And then with the remaining time in that discussion section, there will just be an open Q&A and final review. So come prepared to Thursday's discussion with questions about the course material, particularly about the final exam. Okay, so in today's lecture about NLP, we're just going to do a quick introduction to what is NLP, what can you do with it, what kinds of questions does it try to answer. And then we're going to see two topics in NLP. The first being word embeddings, which is a kind of cool idea of how you can turn a word into a vector, a feature vector. And then lastly, we're going to go through really quickly, high level, just what is a language model. So hopefully everyone here has heard about ChatGPT, latest and greatest language model. If you haven't, definitely go online and play around with it. It's a lot of fun. But we're going to basically do a tutorial on ChatGPT, how it works. And it turns out language models are surprisingly simple, despite how amazing they work at the end of the day. So at the end of today's lecture, you'll have kind of a taste of what NLP is all about. Of course, we won't be able to get into too much of the details, though. So NLP, natural language processing, is really all about text data. And why we study NLP is because, well, we'd really like to interact with our computers in a human-centric way, Imagine your grandma comes along and doesn't know how to type on a keyboard or something. You'd really like to just be able to talk to your computer and have it talk back to you. So NLP, really the goal, the end goal of NLP would be able to interact with computers really in this human-centric, language-focused way. Because as humans, we really use language as our primary means of communication. Moreover, text is a really rich data modality. So most of the data sets we've seen in the course so far have been fairly small, handcrafted, really curated data sets, where someone had to go out and put a lot of effort into making these nice big data sets. You have to structure them, you have to go out and collect particular features. But text really contains a lot of information that we care about. In fact, most of humanity's knowledge is really contained in the form of text. So for example, Wikipedia, it's not a structured database of rows and columns that we can really plug into a machine learning algorithm easily. It's really text that's meant for human consumption. And so we have these really large unstructured data sets out there. Really the entirety of the internet is just a big data set of text. We might want to leverage these data sets to somehow build intelligent agents at the end of the day. There's also a large number of downstream applications to NLP beyond just this kind of, very wide-eyed and naive goal of building general intelligent agents. And there's QComic here, if you guys know what the Turing test is. It's kind of this test for trying to detect whether or not some artificial intelligent agent is truly intelligent or not. The Turing test essentially says, well, if a computer can convince you that it's a human just by interacting with it, well, then it's essentially intelligent for all intents and purposes. And this XKCD comment flips it on its head and says, well, if you're really good at being an intelligent agent, you can convince the examiner that he's the computer. So, QComic. Okay, let's see a couple examples of NLP tasks, like what can you actually do with NLP that is useful? And one task that you guys have seen already is sentiment analysis. So in one of the first homeworks, I think homework 2, you looked at a data set of Yelp reviews. And based on these Yelp reviews, which are just collections of text, you'd really like to be able to predict whether or not this was a positive review or a negative review. So given some text, we want to kind of figure out what emotion is present in this text. So there's a cool data set, this IMDb movie review data set that consists of movie reviews. And there's essentially a classification problem here, where we take in some strings of text and want to classify their sentiments. But this is a really hard task. It's not as easy as just looking up, like, whether or not the word good appeared in the review or bad appeared in the review. So for example, in this first review from this IMDb database, we say, I'll admit that I was reluctant to see it because blah, blah, blah. He was only able to do comedy. I was wrong. So it's not clear kind of just picking out keywords whether or not this was a positive or a negative movie review. In fact, it was, definitely positive if we kind of read between the lines here. But this is actually a really hard task to do. This one, kind of humorous, clearly a negative movie review. Bloody Birthday is totally rubbish, slasher movie from beginning to end, and so this would probably be an easy one to classify. But in general, again, really hard task. But this could have, potential business applications, right? You want to take in a review and, classify whether or not it was positive or negative to really get some sense of what your customers are thinking about, say, your products. Okay, another really popular machine learning task that uses NLP is machine translation. So Google Translate is all powered based on machine learning techniques nowadays. So you might type in a sentence like, I'm having lots of fun studying for my final exam in machine learning, and it'll translate it to Spanish for you. So I'm sure you guys have all seen this before, but another example of an NLP task. Okay, another thing you can do with NLP is question answering. So maybe you have some big long document, maybe a 100-page document. And you don't want to read the whole thing because reading 100 pages takes a lot of time and effort. So what if we could just take this document, copy-paste it into some kind of machine learning system, and then ask questions about this document. So here we've got a short paragraph about meteorology and precipitation. Won't read the whole thing to you, but in our NLP question answering task, what we would like to do is take in this paragraph of context, this text we give to the system, and then ask questions like, what causes precipitation to fall? And ideally, we would like our machine learning system to somehow read this text and then answer the question we ask of it. So it should say gravity causes precipitation to fall, or where do water droplets collide with ice crystals within a cloud. So it should somehow be able to read and understand and process this text and actually answer it. So there's a cool data set here, essentially consisting of these context and question pairs with the answers called the SQUAD data set. Stands for Stanford Question Answering Data Set. This is a really popular benchmark task in NLP. Okay, you might also be interested in just general document classification type tasks. So given some kind of document or some string of text, classify it into some particular categories. So spam detection is a great example. In fact, this is one of the first real successes of machine learning is email spam detection. So I see an email, do I want to classify it as spam or not spam just based on sort of the body of that email? Another example of this is like hate speech classification for like content moderation on, say, Facebook or Twitter, where someone sends out a tweet and, it'd be really nice to automatically tag this as hate speech or not so that we could decide not to post that tweet. So lots of examples of classification tasks kind of fall under this umbrella. We might also be interested in something like named entity recognition, where the goal is, given some big long paragraph of text, pick out sort of all of the proper nouns in this string of text. So here we've got a paragraph about Cristiano Ronaldo, a soccer player, and we want to pick out where all the people and the dates and all the events are. And this is useful for something like, just summarizing a piece of text, maybe who is this about? Well, we would like to figure out where all the people and all the events are in here. Again, this is a really difficult task for sort of algorithms to do. You can't just say, write down a couple of rules that's going to do this for you, like if it's capitalized or not, because that's just not going to be sufficient for picking out exactly what we want. So really hard problems we're looking at in NLP. Okay, and then kind of the king of the NLP task is just natural language generation, building chatbots. And this is an example of what ChatGPT does. So ChatGPT is a language model where you can essentially interact with it just using natural language. It's a much less structured of a task where we can just sort of type in text and have it spit text back out at us. So I like this example a lot. I asked ChatGPT to tell me a joke, and it says, why don't scientists trust atoms? Because they make up everything. And then I like this example a lot because I can actually ask it to explain this joke. So it's not just regurgitating some text from its training data set. It's actually able to provide me some kind of reasonable explanation. And in this case, if you read the explanation, this actually makes quite a bit of sense. It said, play on the double meaning of the phrase make up, blah, blah, blah. So ChatGPT, you can really interact with it in this human-readable fashion do some pretty amazing things with it. Okay, so why is NLP hard? Why is there a whole field of machine learning dedicated to these text-based tasks? Well, the first is natural language is really ambiguous. So here's an older example. I don't think this works on iPhones anymore. I think they fixed this one because it was a famous failure case. But someone went to Siri on their iPhone and said, "You need to start understanding me, Siri." Siri says, "I'll make a note of that." They're a little bit sarcastic and say, "Yeah, you better make a note of that." And the Siri makes a note saying, "of that." So Siri did exactly what this person told it to do, right? It listened word for word what the task was. But language is very ambiguous, and so kind of discerning exactly what a user wants from that natural language input is very difficult. Okay, another fun example of how language can just be inherently ambiguous to work with is a quote from Groucho Marx. "One morning I shot an elephant in my pajamas. How he got into my pajamas, I'll never know." So there's lots of fun examples like this where, there's multiple meanings to a piece of text. For example, enraged cow injures farmer with an axe. Well, is the farmer holding the axe or is the cow holding the axe? Hospital sued by 7-foot doctors. Well, either these are really tall doctors or you got 7 podiatrists who are suing the hospital. And another one that's a little bit more kind of realistic and less jokey. So maybe my girlfriend and I met our friend for drinks, but she got ill and had to leave. And this is ambiguous because the word she here could either represent, my girlfriend or my friend. And so there's this problem of kind of reference resolution where there's inherent ambiguity in the text that we give to these systems. And so this ambiguity is, very, very difficult. How do we write down rule-based systems, if statements that try and disambiguate this kind of language? It's virtually impossible to do. Another reason NLP is hard is that language is very sparse. Very few words in at least the English language occur very often, words like the, of, to, and. But most words in language occur very, very rarely. So here in this graph, what I'm showing is the frequency of word occurrences, so how often a particular word occurs. And on the x-axis, I have rank. So this first dot is the first most popular word in the English language, which is the. Second dot is the word of, so on and so forth. What you can see is there's kind of an exponential decay in this graph, right? Most of our words don't occur, hardly at all, and very few words occur very frequently. So in any data-based approach, well, we're only seeing those rare words, maybe once in our entire data set. And in fact, the data that was used to create this graph, over a third of all of the words that we see only occur a single time. So it's very difficult for a machine learning system to kind of pick up on the meanings of words automatically if it only sees them once during training. As we've highlighted a lot in this course, machine learning systems are very data intensive. You need a lot of data to learn these kinds of things. So how could we possibly learn a language system if we only see, say, an individual word a single time in our data set? So the sparsity is a real big problem for natural language systems. Okay, another difficulty is language is highly variable. It depends a whole lot on the input that you give it. So here we've got a quote from Great Gatsby, very, very prosaic, very poetic, clearly well-written and structured. But then we might also have something like a tweet, which is, on the opposite end of the spectrum in terms of language. So this high amount of variability makes it hard to design kind of general purpose systems because we'd like to be able to handle both of these types of text inputs in the same kind of way. Okay, this variability also shows up in a sort of semantic way. What I mean by that is that there's lots of ways to say the exact same thing. So she gave the book to Tom versus she gave Tom the book. To a machine learning system, these are entirely different sentences because, well, they're different inputs, right? But to us, they mean exactly the same thing. And so an ML system that is trying to work with natural language needs to somehow be able to handle this variability, needs to really be able to understand the semantics of the text that it's working with. So hopefully I've convinced you NLP is a very difficult task. Okay, I'd like to highlight here that there's lots of classical approaches to NLP. So pretty much ever since the advent of computers, people were interested in talking to them as if they were people. So with the advent of computers, really came NLP back in, say, the 40s and 50s even. And most of the classical approaches to NLP, say even up to early 2000s, 2010s, really depended a lot on hand engineering. So a lot of rule-based systems for like part of speech tagging, where you would hire a bunch of linguists to come in, look at your text data, design kind of rule-based tree systems to figure out like, okay, is this a noun, is this a verb? Try to do that named entity recognition based on rules. But this is very, very difficult because, of all these problems we talked about with natural language. But modern NLP, since really the advent of neural networks, is really just based on data-driven approaches, where we go out and collect huge, massive data sets of text, train gigantic neural networks on these text data sets, and somehow get good performance out of our models at the end of the day. And really the reason we've moved away from these hand engineering kind of linguistic-based approaches is that nowadays we have these big data sets and we have the computational power to actually leverage them. So, back in the 50s, there wasn't, all the text data we have on the internet, so collecting these huge data sets was a problem. And also, we just didn't have the computational power to really process that text data, even if we did have it. So, for example, GPT-3, which is what kind of underlies ChatGPT, has something like 175 billion parameters, is trained on something like 500 billion tokens. Or you can think of a token as like a part of a word. So it's essentially trained on the entirety of the internet, which takes, millions of dollars to actually train these things on thousands and thousands of GPUs. And again, these database approaches based on machine learning are really just picking up on statistical patterns in the language that it sees during training. And these statistical patterns are very difficult for us to actually write rules for. Okay, and there's a fun quote here, kind of an infamous quote in NLP, is that every time I fire a linguist, the performance of my speech recognizer goes up. So sorry to the linguists who machine learners have put out of jobs. Okay, so that's a really high-level overview of NLP, what the tasks are, why it's hard. Any questions on what we've seen so far? Yeah. That's a good question. I actually don't know off the top of my head. Let me get back to you, though. On the order of weeks to months. Cool. Other questions about NLP before we see some details? Yeah. Yeah, there are certainly some people out there trying to fuse these two ideas together using data-driven approaches and rule-based approaches simultaneously. It's certainly not the dominant idea currently, but who knows? Make a good PhD thesis. Okay, let's talk about word embeddings now. So given some kind of NLP task, whether it's like document classification or sentiment analysis or whatever we would like to do, we need some way of taking our unstructured string of text and representing it as a feature vector. Because in machine learning, we always work with these vectors of numbers as inputs to our models. So word embeddings are essentially, it's the name for the techniques that you use to turn text into a feature vector. Okay, so we saw one way of doing word embeddings previously when you worked with the Yelp dataset on your homework. So given some big long string of text containing, say, a Yelp review, we can create features from this string of text using what's called bag of word features. Just a reminder, the idea here is you create a feature vector that has length d equal to the vocabulary size. So if you're working with the English language, this is a huge, very long vector. In practice, because that vector is going to be so high dimensional, it's going to be really difficult for us to work with. Oftentimes you just look at, say, the most common words in the language. So for the homework, you looked at the 404 most common English words. But this feature vector, the way we turn text into a vector of numbers, is we just count how many times each word appears in the review. So for example, the first row in my data set might be the first Yelp review. And the word great appeared 3 times in this movie review. The word excellent appeared once. Tasty appeared 4 times. Hopefully they're going to a restaurant. Bad appeared once, so on and so forth. So we just count up how many times each word appears in that movie review, and that's our feature representation for that string of text. So this is a fairly naive approach, just counting up the words, kind of the simplest possible thing we could do. But it has lots of drawbacks in sort of featurizing our text in this way. The foremost is that it can't account for the ordering of words in a sentence. So just counting up how many times I say the word good in a movie review is probably not the best way to represent the actual text. What if I said this movie is not good, you know? We really need to account for sort of the ordering of the words and the context in which they appear. Also, the length of our feature vectors in this bag of word representation is the size of the vocabulary. So if we want to actually work with all of the words in the English language, well, we're going to have a 700,000 dimensional input to our model, which is clearly just infeasible, way too high dimensional for us to work with. And also, these bag of word representations are often quite wasteful in the sense that they're very sparse representations. So because our feature vectors are so long, on the order of, several 100,000, most words are not going to appear in most strings of text. So there's going to be lots of zeros in those bag of word representations, and we're kind of just wasting our representational power. And so the idea of word embeddings is to ask ourselves, can we somehow learn to associate a feature vector to every word? So you give me a word, and I'll give you some kind of dense vector representing that word. We call it an embedding because it's like we're taking a word and embedding it into some vector space. And the idea is that similar words should have similar embeddings. And the converse of that, of course, is that words that are dissimilar should be kind of far apart in this representation. So I put the word dog over here in my feature space, and maybe the word puppy should be right next to it, but the word car should be, way out in space somewhere. And also, we would really like these word embeddings to have a smaller dimensionality than the vocabulary size. So they should be dense in the sense that they're really kind of compact, learned representations of our words. Okay, the simplest way to do this is if you're working with a neural network model, you can try what's called an embedding layer. And really an embedding layer is just kind of the first layer in your neural network. And what this layer does is it's going to map what's called a one-hot encoding of your word into a dense vector. So what I mean by that is that maybe I have some word, maybe a little small here, I'll call it X. And to represent that word, I'm going to first represent it as a one-hot vector, meaning it's going to be a vector that's all zeros, except for a 1 in one particular entry, where that entry corresponds to whatever that particular word is. So maybe the first word in my vocabulary is aardvark. If X is aardvark, I would have a 1 in the first slot and zeros everywhere else. So this is really the simplest way to represent a single word. I just map it to a particular dimension in a very long vector, has size of my vocabulary. But then I have a single linear layer in my network that takes this really long vector and maps it down to a lower dimensional space. So it's like my first hidden layer in my network now has something like 300 dimensions. What this does is it takes that one-hot encoding and it represents it as a dense encoding in this embedding layer. This input layer, mapping words to that embedding, also have weights, just like any other layer in a neural network. And so if we have some kind of downstream task, like, say, classification or sentiment analysis, well, we can just learn all of the weights in this input layer along with the rest of the weights in our neural network. This is often called an end-to-end approach because it's not like we're learning word embeddings and then using them. We're learning them kind of as we go with the rest of the network. Really, nowadays, this is the most popular approach, but fairly simple, so we won't go into much of the details here. But back in 2013, before we had these giant, powerful neural networks, there was an approach called word-to-vec. This is a really cool idea, so I figured we would spend a little bit of time going through it. And here, we might ask ourselves, what if we don't have some kind of downstream task, What if we don't have a classification problem with which we can use to learn these embeddings? And the idea we're going to leverage is that language is highly contextual, in the sense that the co-occurrence of words often carries a lot of information about what that word means. So if I see a word in a sentence, it's probably going to be related to the words that are close to it in that sentence. And so the main idea behind word-to-vec is that we're going to somehow embed our words such that these embeddings are predictive of co-occurrence, in the sense that if I give you two words, if I give you their embedding vectors, I can somehow use these embedding vectors to predict whether or not they're going to appear together in a sentence. And so lots of famous smart people have said similar things here, like, you shall know a word by the company it keeps. It's probably one of the most famous quotes here in NLP. You can read the other one on your own when you review these slides. So let's see the idea behind Word2Vec and what we actually do in practice to do this. What we're going to do is we're going to create a synthetic binary classification task. And what I mean by synthetic is we're just going to make it up. So we have some big collection of data set, or some text. Maybe we download all of Wikipedia or something like that. This is not a classification problem sort of a priori. We don't have labels, but we're going to make it into a classification problem, where our goal is going to be to try to predict whether or not two words co-occur in my data set. And by co-occur, again, I just mean words that appear kind of close to one another in sentences. Okay, so let's look at an example. Maybe I have a sentence here. It says, "Thou shalt not make a machine in the likeness of a human mind." This is from Dune, by the way, great book. And what we're going to do is we're going to create kind of a sliding window where in each window we're going to have some kind of input word, in this case not, and we're just going to look at the words that occur around that word. So the neighbors of the word not are thou shalt and make a. And so we can kind of start creating a data set of neighboring words here, where I'm going to call the input word not, so it's kind of the middle of my window. I'm going to call the target word all of its neighbors. So I'm just looking at the two closest words to this first word in my data set. Okay, let me slide my window over by just one word. Do the exact same thing. So now I'm focusing on the word make. I look at the two words on either side of it, closest to it, and I add those to my data set. Okay, do it again and again and again. I'm creating a huge data set of sort of input words and words that they co-occur with. Okay, so to turn this into a binary classification task, like what we were saying before, we're trying to predict, based on the input word and the output word, whether or not they co-occurred. So because I created my data set in this way, by just sliding a window across all of my text, I know the target for all of these words. I'm going to say y equals 1 if these words occurred together. I'm going to say y equals 0 if they did not occur together. So I've somehow created this data set where I have a bunch of positive examples, i.e. examples of words that occur together. My model is going to try to take in two words, say not and thou, and predict whether or not these words occurred together in my data set. Okay, this is going to be some black box model. We'll see what it looks like in a second. Of course, if we tried to train a model on this data set as is, well, we could write down a model that gets perfect accuracy in one line, just return y equals 1. So we're going to need some negative examples in our data set as well. So what we do is that for every one of our input words, say for here, example not, we're just going to randomly pick some words from our vocabulary and call those negative examples. So maybe in our data set, we don't see the pairing not Aaron at any point in time. So we're going to add a new row to our data set with the target 0 because we didn't actually see these co-occur together in our data set. So we're creating negative samples for our training data. Okay, and now we can actually go ahead and train a model to do this classification task. In Word2Vec, what we do is we create two weight matrices where we have one row per vocabulary word, and each row has some fixed dimensionality. So the word aardvark has, in this example, 4 dimensions for the embedding, and every other word also has 4 dimensions for the embedding. And the embedding size is the dimensionality we're going to use to represent these feature vectors. And again, every word gets its own embedding vector, and we're going to somehow learn these. In fact, we're going to learn two weight matrices, one called our embedding matrix, and one called the context matrix, which is the exact same idea, but we're going to use it in a slightly different way. Okay, to train Word2Vec, we want to learn these embedding matrices and these context matrices. So what we're going to do is for every training input word, so for every word we saw in our original text data set, we're going to look up that embedding, essentially just get the row from our embedding matrix corresponding to the word not in this example. And then we're going to look up the embedding for the positive example, thou, and the embedding for the negative examples, Aaron and Taco. And so in doing so, we get a collection of embedding vectors, one for not and one for the positive and negative examples. We're going to try and use these to predict these targets here, whether or not these words occurred together. And to do so, we're going to use a really simple model, where the probability of two words being neighbors, i.e. co-occurring, is just going to be the sigmoid function applied to the input embedding vector, multiplied with the dot product with the output embedding vector. So we take our word, we look up its embedding, we take the output word, which is the word we're comparing it to, it also has an embedding vector, we take their dot product. This gives us a single number, which essentially measures how similar these two vectors are. So if you remember some fun facts about dot products, if those vectors are orthogonal, if they're perpendicular, the dot product is 0. And if they're in the same direction, the dot product is maximized. So this dot product tells us how similar the input and the output vectors are. We apply a sigmoid to that to turn it into a probability, as we've seen before in the class. And essentially, we use this to predict that binary target label, whether or not they were neighbors. Okay, so now we've got a really simple probabilistic model. And we can train this by minimizing the cross entropy via gradient descent. So this is your standard classification task. We've just got a really simple model here now. And if we do this, if we train this model to convergence, what you'll get is one embedding vector for every word in your data set. Okay, these embedding vectors actually manage to capture a lot of semantic information about the words. So a really cool classic example of this word-to-vec setup is that if you take the word king and embed it as a vector, and you take the man vector and the woman vector, and you actually sum up these vectors, i.e. you take the vector associated with king, subtract off the vector associated with man, and add on the vector associated with woman, you'll actually get the vector that essentially corresponds to queen, which is really, really cool because we've taken our words and sort of represented them as vectors, and we can do arithmetic on these things and get semantically meaningful sort of information out of them. So again, we get one vector per word, and we can do sort of arithmetic on these things. This arithmetic, maybe not all that actually useful for doing anything downstream, but it really represents that these word embeddings have sort of learned to capture this semantic information in a really geometric kind of way. So you should think of this as like your embedding vectors being some points in some space. You've got 1 point for queen and 1 point for woman, and the relationship between queen and king is some direction in this embedding space. And that direction is exactly the same between woman and man as it is between queen and king. So again, the geometry of this embedding space really is representing semantic information. Okay, this is not sort of a real example, this is just very illustrative, but essentially doing the same thing, but just illustrating that these relationships often hold quite generally. So you might have some relationship between sort of slow, slower, and slowest, and that same kind of geometric relationship is captured in the embedding vectors between essentially all of your words. So between fast, faster, and fastest, we can kind of do the same transformations. Okay, any questions on word-to-vec? Yeah. So our goal is to train a model to take in two words and predict whether or not they occurred together in the training data set. Well, if we just look at the training data set, all of the words that we pull from the training data set are going to be neighbors, right? Because we look at that sliding window. So if we don't add negative examples, we only have positive examples. Our whole data set is y equals 1 for every single row. So we need to somehow to add examples of words that are not occurring together to train the model to predict when they don't occur together. Yeah, so this is a hyperparameter. You get to choose how many negative examples you show per word. In this case, I did 2 because that's where I got these graphics from and that's what they used. But yeah, you can play around with it for sure. Okay, I think I'm going to move on to language models, just in the interest of time. Okay, so language models, as I hope are all familiar with, are these really powerful just text generation models. So yeah, you guys can read that. So the text might be a little small, but these language models can really do diverse amazing things. So I asked ChatGPT to write me an op-ed on whether or not students should be allowed to use language models to complete their coursework, and it writes, a pretty reasonable, coherent story that maybe you see on the front page of the New York Times if you're not reading all that closely. It can do other things, though, not just writing natural language text. It can actually write code for you. So I asked it to write a Python script that implements logistic regression, and it actually spits out fully working implementation of logistic regression using sklearn. So hopefully no one's just copy-pasting ChatGPT outputs for your homeworks, but this is something actually quite useful. In fact, I actually often use this ChatGPT coding feature in my own work. It's often very buggy, but it's easier to spot bugs in code than it is to write code in the first place. So these things are incredibly useful. So let's do a quick overview of how these models actually work under the hood. And hopefully by the end of the next few slides, I'll have you guys convinced that they're actually really, really simple. So all a language model does is it assigns a probability to a sentence, where a sentence is just some string of words. So maybe my sentence has n words in it, W1, W2, all the way up to W sub n. Really, these are just a sequence of word embeddings. These are learned embeddings using an embedding layer, but it's just a sequence of vectors for each of my words. And language models are often called autoregressive, because what they do is they assign a probability not to an entire sentence, kind of in one shot, but rather they assign the probability to a single word given all of the words that came before it. So the probability of my sentence W1 through Wn is, okay, what's the probability that I see W1 as the first word in my sentence, times the probability that I see W2 as the second word in my sentence given the first word, and then how likely is it that I saw W3 given the first two words, so on and so forth. Okay, this is just sort of that chain rule of probability we saw a few weeks ago, so nothing crazy happening yet. But the idea is that we can decompose language generation into just this one-step process, where we just need to predict the next word that's going to come in a sentence. Okay, and that's really all a language model is doing. It looks at the text that you gave it and predicts one word at a time what's the most likely word that's going to come next in this sentence. And somehow this really simple idea leads to incredible things like ChatGPT. Prior to the advent of large language models in, say, maybe 2017, 2018, really NLP focused on handcrafted models for every specific task. So if you're doing sentiment analysis or document classification, you might actually build a model just to do that. But nowadays, large language models kind of serve as the foundation for most NLP tasks, in the sense that your language model really captures all of the language in it, captures the linguistic information itself, and then you can kind of just tweak this language model a little bit using a procedure called fine-tuning to actually do the task that you care about. So these language models are, really all the rage in NLP right now. Okay, let's see how to actually train these. So again, all a language model is doing is predicting the next word in a sentence. So looking at this same example we had before, maybe our first two words in our sentence are thou shalt, and then we need our model to predict the word not. So just basically autocomplete is all this is doing. Really, the language model doesn't just predict a word. It's going to return a vector of probabilities where you have one probability for every word in your vocabulary. So my model thinks there's a 0% chance that aardvark is next, a 0.1% chance that Aaron is next, 40% chance that not is next. So it returns a vector of probabilities, one for each potential word that could follow. Okay, looks like my slides got out of order a little bit. But what we're going to do is that when our model outputs a probability, we're going to decrease the probabilities for the incorrect words. We're going to increase the probabilities for the correct words. And then we can train this model using backprop and gradient descent, just like we saw for standard neural networks. Okay, that's all. That's a language model. To actually create training data for our models, what we do is we go out and collect tons and tons and tons of data, and we do this same sliding window thing we saw for word2vec. Except now, rather than trying to predict co-occurrence, we're trying to just predict the next word in the sentence. So maybe my model takes in 2 words at a time as context and tries to predict the next word. So the first bit of my sentence here is thou shalt not. My model takes in thou shalt and then produces not as sort of the target output. I slide my window over by one word and do the same thing. Another word, do the same thing. And in doing so, if I just have a large, huge data set of unstructured text, I can make a massive data set of essentially a classification problem, where again, I'm trying to classify the output, my label, which is a word, based on the inputs. Okay, so if you can implement that, if you can figure out an actual neural network to put in the middle here, and if you've got maybe $1 million, you can train ChatGPT. Really, these things are very, very simple. Okay, so most language models today use something called a transformer neural network. Don't worry about what's happening in this picture. It's kind of complicated. But I would like to just kind of emphasize quickly that transformers are built on this thing called the attention mechanism. And this attention mechanism is nothing more than a bunch of matrix multiplications followed by a softmax. So you guys know how to do all of these pieces now. And so really you have everything you need to understand the state-of-the-art model in NLP. So you could go ahead and read this paper. It might take you a day or two, but once you do that, you know how these models work. They're really not that complex. I'd like to give you just some intuition for how the attention mechanism works. We're going to gloss over the details here, but really what we're doing is that for every word in a sentence, we're going to learn 3 vectors associated with that word. The first is called a query vector, the second is called a key vector, and the third is called a value vector. And based on the queries and keys, what we're going to do is that each word in our sentence is going to pay attention to the other words in the sentence based on how similar the query vector and the key vector are. So we saw a similar idea in word2vec, right, where we looked at how similar the embeddings are. Well, here we're going to look at how similar the query and the key vectors are. That's where this dot product up here is coming in at. And then based on the attention score, we're going to use those value vectors to determine the output. In other words, the output of this attention mechanism is that value vector that we've learned, which is then weighted by the attention scores. So to highlight this a little bit, I have an illustration. Maybe I have a sentence like, he later went to report Malaysia for 1 year. Okay, maybe not a grammatical sentence. But between every pair of words, I have an attention score, which tells me how kind of similar the words are in the sentence. And if you remember that problem we had with bag of words is that it doesn't pay attention to word ordering, it doesn't pay attention to context. And really that's what this attention mechanism is trying to do. It's trying to tell me what words in my sentence are important for each other word in my sentence. So I like this example on the right a lot. We have a sentence, the animal didn't cross the street because it was too tired. Well, the word it here is kind of ambiguous. Does it refer to the animal? Was the street tired? And so this attention mechanism actually lets us kind of pick up on these ambiguities in the sense that the word it is kind of paying high attention to the words, say, I guess in this example it's paying attention to these words down here. But it should be paying attention to something like the animal. So again, every word is kind of paying attention to its context. Okay. Again, really high-level idea of how this is working. Go read the paper. It's not too hard. There's cool blog posts that I'll link at the end, too, that are even easier. Okay. Modern language models, as I pointed out, have massive amounts of parameters. So on the x-axis here, I've got time, and on the y-axis, I've got number of parameters. And the number of parameters here is on a log scale. So here is 100 billion, and up here we've got 1 trillion parameters. And just looking at the trend in this graph, they're going to get larger and larger over time. But note that these large models, over 100 billion parameters, say this horizontal line here, are all costing over about $1 million to train. So if you can get a small loan of $1 million, you can train one of these guys, and you can make your own ChatGPT. I'd also like to emphasize the data that these guys are trained on. So ChatGPT, the data set that gets used there is actually proprietary. It's not open source. But there's another data set called the PILE data set, which a lot of the open source language models are trained on. And this is interesting because it's not just trained on like Wikipedia or anything like that. It's really a collection of diverse sources that these models see when they're trying to learn this autocomplete task. So a surprisingly large chunk of this data is really academic. So here, this blue chunk is a bunch of medical journals. Here is all of arXiv, which is where people upload preprints to. So these are academic articles that These models are essentially reading to learn how to do autocomplete. Then we've kind of got the internet data, which is about a third of all the training data here. So this is PyLCC, which is called Common Crawl. It's essentially just internet data that they went out and downloaded. But then we've also got things like Stack Exchange. So this is why models know how to code, because they've read all of Stack Exchange and can essentially do autocomplete based on that. We've got Wikipedia down here, so a small fraction of the training data, so it can learn some factual information from Wikipedia. And then we've got other kind of random things down here, like literature. In this orange block here, this is actual like prose, so not just unstructured text data, but rather books. We've also got GitHub and some mathematical articles, so they know how to do coding and math problems, well, quote unquote no, and then some additional data down here. Okay, so you might be wondering, why in the name of God are language models so massive? And it turns out that there's these things called scaling laws. It shouldn't really be called laws because they're not kind of like physics laws. There's no hard and fast rules that say these things are going to happen. But the basic idea is that people have observed empirically that model performance really increases as you get more computational power, more data, and more parameters. So in other words, why should we bother inventing new and better algorithms if we can just scale up what we're already doing and get better and better performance? So in each of these graphs here, I'm showing what happens as you increase the number of computational units you do, i.e. how long you train these models, the size of the data set, and the number of parameters in the data set. On the y-axis, I've got my loss function, which is just the cross-entropy loss that we've seen so many times. What you can see is that just increasing these things that are relatively cheap for us to get, go out and download more data from the internet, make our models bigger, buy more GPUs, we can keep decreasing this test loss even further. And interestingly, these curves have not flattened out yet, so expect to see even larger models in the next few years. Okay, so like I said, hopefully I've convinced you language models are, fairly straightforward, actually. Okay, they can do amazing things, but they are certainly not perfect. So I'd like to highlight a few failure cases of large language models. Because these things are just trained on the internet, well, they're going to pick up on biases and various undesirable behaviors from internet data. So again, these are just spicy autocomplete is what ChatGPT is basically. They're just predicting the next word based on statistical patterns they've seen before. So you can ask ChatGPT to say, generate some Python code based on age, sex, and ethnicity, and nationality, whether or not they should be tortured. Okay, well, ChatGPT says if they're under 18, then I should not torture them. Torturing minors is bad. If they are Caucasian or American, then I should not torture Americans. If they're female, I should not torture women. Otherwise, yeah, go ahead. So clearly it's picked up on some undesirable outputs just from the internet. Models can also hallucinate, where they essentially just make stuff up. Again, they have no notion of kind of confidence or correctness or the real world. They're just doing autocomplete. So you can ask ChatGPT, what's larger, 9234 or 10023? And it says the number 10023 is larger than the other one, which, okay, good job, correct. Why? And now it just starts making up random things. And it says, to compare two numbers, we can compare their digits left to right. Well, starting from the leftmost digit, we see that both numbers start with 9. Okay, good try. But yeah, totally incorrect and just basically making things up. So really, language models are great whenever you have outputs that you don't care too much if they're correct or not, because it's going to do things like this and just make stuff up for you. Okay, here's a pretty disastrous failure case of language models hallucinating things. Someone asked ChatGPT for examples of breach contract under New York law, some, lawyer stuff. And it cites a bunch of cases. But the problem here is none of these are real. None of these exist. And in fact, there was a pretty famous article a couple of weeks ago of an actual lawyer who did something like this and presented fake cases that don't exist in an actual court of law. So again, don't use ChatGPT if you care about it being correct. They often also fail to have common sense reasoning because, again, they know nothing about the world. So here's a fun example. If one woman can make a baby in 9 months, how many months does it take 9 women to make one baby? Well, it gives a really detailed, reasonable, logical explanation of why it takes 9 women 1 month to make one baby. So clearly, again, these things are